All right, so we had a test on graphing last week, where we were graphing with H and K. You will not get to do test corrections on that test. So just know that. Oh, whenever it gets taken by everybody. Today and throughout the rest of this semester, we'll be throwing in graphs of new functions that you haven't seen yet. And so you can expect the same sort of shifts with H and K. And we're going to do that today with exponential growth and decay. So just to remind us about exponents, what is 2 to the 4th power? What does it mean?
2 times 2 times
2 times 2. Good. And what is that? 16. Okay. And again, this is something you can put into your calculator, right? 2 caret 4 equals 16. So make sure that you know how to put those things into your calculator. What does a negative exponent do? It turns it into a fraction. That negative exponent says, hey, drop me down to 1 over 3 squared, which would be 1 over 9. And again, you can put that into your calculator as well, and it'll give you some crazy decimal, but then you want to math frac it, and it'll give you the fraction 1/9, okay? And then this is 1/2 to the negative 3 power. So yeah, you can turn it into a fraction, but that gets really, really complicated. So one thing that we can do is actually the negative, if we have a fraction, it's the reciprocal. It's just going to flip the fraction. Yeah, so we could write it this way, but that gets really complicated. So if we have a fraction already, we just need the reciprocal, which would flip that. So it'd become 2 to the happy 3rd power, which would give us 8. And again, this is something you could put into your calculator. 1 divided by 2 to the negative 3 power, and it'll give you 8. Ladies and gentlemen, you should be using your calculators. You should know how to use your calculators. There's absolutely no reason for you to get the scores that happened on the test, because it was all graphing, so it should have been easy to do if you would be, plugging things into your calculator like I told you to do every single day. When in doubt, graph it out, use your calculator to check. All right, make a table of values to graph the function. Not example 1, just talking about these graphs. Make a table of values to graph the function. So whenever you're graphing functions, it's x's and y ordered pairs. And so we can always graph things by creating a table of values. I'm going to say 2 to the x equals y. And so all we have to do is pick values for x and plug them in and see what happens. And so we're going to do -2, -1, 0, 1, and 2. Always really good values to start with anything. And if you have your calculators, you might want to get those out so that you can just use calculators to find out these things and make sure you know how to use your calculator. For the rest of this semester, you must have at least a scientific calculator. You will not be able to calculate these problems without at least a scientific calculator. So if you don't have one, you need to get one from the finance office. All right. So I'm going to plug -2 in place of x. So it's going to be 2 to the -2 power. What do you get? 1/4. Yes, that would be 1 over 2 squared, which would be 1 over 4. And again, plug that into your calculator and math frac it. We would have 2 to the -1 power. What's 2 to the -1? 1/2. we're going to plug in a 0 for x. So that's 2 to the 0. What is 2 to the 0? Ooh, plug it in your calculator, please. It's 1. It is 1. Always, always. Any number to a power of 0 always equals 1. And when in doubt, use your calculator. That's what it's for. All right, then we're going to plug a 1 in for x. 2 to the first. 2. Going to plug a 2 in for x. 2 squared. 4. All right. So these are some great values to get started. Okay, so at -2, we have the value of 1/4. So that's just a little bit above the x-axis. At -1, we have a value of 1/2, just up halfway between 0 and 1. 0, 1, 0, 1 is right here. 1, 2, and 2, 4. And you can imagine if we plugged in a 3, it'd be 8. And if we plugged in a 4, it'd be 16. This graph is growing, what we say, exponentially. It's growing very fast. I want to think about what it's doing to the left here. I'm getting 1/4, or 1/2 and 1/4. If I plugged in -3, I'd get 1/8. If I plugged in -4, I'd get 1/16. If I plugged in -5, I'd get 1/32. What's happening as we move to the left? It gets closer to the axis. It's getting closer and closer to 0. Basically, smaller and smaller fractions. 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. It's just getting smaller and smaller. Is it ever going to get to 0, or are they just going to keep getting smaller and smaller fractions? Smaller and smaller fractions, okay? So what we have then is this function is getting closer and closer and closer and closer to the axis. Is it ever going to touch the axis? No. In fact, it gets infinitely close because we just keep getting smaller and smaller fractions. So it turns out that all of these graphs have a horizontal asymptote. Right now, this horizontal asymptote is at y equals 0. Horizontal line at 0 on the y-axis. This is what we call an exponential graph. We also call it exponential because the x is in the exponent. That makes it exponential. So we call these exponential functions. This is called exponential growth. Why do you think it's called exponential growth?
It's growing.
It's growing. As we move to the right, our graph is getting larger and larger and larger. This is exponential growth. I lovingly call this the Superman graph. Have you been to Six Flags Magic Mountain?
No. What's 6 Flags?
So at Six Flags Magic Mountain, they have a ride called the Superman. It's the stupidest ride on earth.
Isn't it the scariest ride too?
No, it's just stupid. And boring. But you sit in this like trough of people, like 15 across, and there's like 3 rows. And basically the hydraulics just compress and compress and compress, and you sit there and it just goes zoom, zoom, zoom. And then it zooms off. It's the hydraulics just shoot you up this ramp. And the ramp is this curve. It is y equals 2 to the x. It is this exponential function.
Were you like on the ride, like, oh, this is this curve?
No. I wasn't a teacher when I went on the Superman ride. So no, it didn't occur to me at the time.
Was the drop scary?
And then you just fall back down. But yeah, it's over in like 3.5 seconds. So it's just really not super cool. But anyway, I lovingly call this the Superman graph. Superman to the moon. They grow very, very quickly. So this is exponential growth. And we want to talk about the domain of this function. Look at these arrows. How far to the left and how far to the right do these arrows go? Infinite. Negative infinity to positive infinity. What about the range? How low? What is our lowest y value? Well, it doesn't ever get below 0, does it? Like, we don't get into negative territory here. Okay. So it actually is 0 is the lowest y value, and it goes up forever. Do we equal 0? No, it gets really, really close to it. So we actually use a parenthesis at 0. We're getting closer and closer to 0, but we're never actually going to equal 0 because it's just a smaller and smaller fraction. The reason we can't equal 0 is because we have a horizontal asymptote at y equals 0. And we're never going to touch the asymptote. So we use a parenthesis at 0. And so this is an exponential growth model, and they all kind of have this Superman shape. And so, you know, I like to give everything silly names. So this is the Superman graph, Superman to the moon. And that's the shape that we'll talk about when I ask what does this look like. So x is in the exponent is an exponential function. What do you think is going to happen when my base changes from a 2 to a base of 1/2?
I think it's shortening to that.
It's going to flip it. How does it flip it? Like, does it flip it like this way? Yeah? Let's see what happens. All right, so again, I'm going to make a little table of values. 1/2, to the x equals y. And I'm going to plug in -2, -1, 0, 1, and 2 just to get us going here. So we have 1/2 to the -2 power. What's the negative going to do to this fraction? Flip it. So it becomes 2 squared, which is 4. All right, 1/2 to the -1 power. Again, what does the negative do to the fraction? Flips the fraction and then turns the exponent positive. So we get 2. What's 1/2 to the power of 0? 1 always. 1/2 to the first power is 1/2. And 1/2 squared is 1/4. 1/2 times 1/2 is 1/4. Well, all right, let's see. So a little sketchy poo here. -2, 4. -1, 2. 0, 1. 1, 1/2. 2, 1/4. 3, 1/8. 4, 1/16. 1/32. What happened to this graph? Did it flip vertically? It actually spun around this way. This is what we call exponential decay. Decay means, we talk about exponential decay when we talk about like radiation. In that the radiation starts really high, like after Chernobyl, the whole nuclear disaster. The radiation starts really high, but as time goes by, as time passes, the radiation decreases a little bit, usually by half every so often. And so we get closer and closer and closer to 0 as time passes by, but we'll never actually get less than 0 radiation. We just get closer and closer to 0. So this is called exponential decay. I call this Superman coming in for a landing. So from the moon comes into landing on the ground, so to speak. Doesn't get below for now. Again, we're getting closer and closer to 0. So there's this horizontal asymptote at y equals 0. And let's talk domain. How far left and how far right do these arrows go? Infinite. Negative infinity to positive infinity. The range, the lowest y value again is 0, and the highest is infinity. So 0 to infinity, but we can't ever touch either of those because we have a horizontal asymptote at y equals 0. All right, so these are exponential growth and exponential decay. And maybe we can see that it's growth because of the base being 2 versus here the base is 1/2. So we get growth when our base is greater than 1. And we get decay when our base is between 0 and 1. All right. So that's kind of a nice hint for what the shape should be. Knowing what the base is tells us whether it's growth or decay. All right. Now, the nice thing is, once we know the basic shape, I don't have to work nearly as hard to graph these functions. So example 1, we're going to graph the core and then shift it, just like we have been with h's and k's. And so I'm going to go ahead and just show you what the standard form looks like right now. Y equals b to the x minus h plus k. This is our standard form for our graphs. I don't know that I have any negatives. No, okay. Our exponential, you can see the x is in the exponent, so it's exponential. So our core function, we're going to make a small, teeny tiny xy chart, just with b to the x, whatever the base is, and then we just get to shift it h and k units. What does h do? How does h shift? Left and right. Again, the h is upstairs with x, and so it's shifting in the x direction, left and right. And the k goes up and down, just like it did before. So what I'm going to do is I'm going to graph the core, or the basic shape here, just graphing 3 to the x. And once you get this, you don't have to do very much. Is this going to be exponential growth or exponential decay? Growth. How do you know it's growth? Because b is greater than 1. The base is greater than 1. So all I'm going to do is do 2 values for x. What is 3 to the power of 0? 1 every single time. What's 3 to the first power? 3. So I have 0, 1, and 1, 3. And this is my 2 basic points for my exponential growth curve. So this is the Superman graph, and this is our basic graph that I get to shift. So every single time these points come out real easy. Do you think you have to do an XY chart for those? No, they're pretty easy every single time. Okay. Then we're going to take these 2 values in our exponential growth curve and we're going to shift them. What does x minus 2 do to the graph? Right 2. Good. Right 2. And what does the minus 4 do? Down 4. So I'm just going to take each point and I'm going to count. Right 2, down 1, 2, 3, 4. Right 2, down 1, 2, 3, 4. Now, my asymptote was here at 0, and it got shifted right 2 and down 4. Where is it? Negative 4, yeah. So that asymptote is right here at y equals negative 4. Draw that in first, and then you can draw in your curve. The exponential Superman graph. What's the domain of that blue graph? How far left and how far right? Infinity, negative infinity to positive infinity. What's the range? How low does it go? Negative 4. Look at that. It goes down to negative 4 all the way up to infinity. Do we equal negative 4? Use a parenthesis because we have an asymptote at y equals negative 4. All right, let's try another one. We have y equals 1/4 to the x plus 1 plus 2. I'm going to start just by graphing this core function, and I can make a little xy chart, very little xy chart. 1/4 to the x, and I'm just going to plug in 0 and 1. What is 1/4 to the power of 0? 1 every single time. What's 1/4 to the first power? 1/4. Is this exponential growth or exponential decay? This is decay because b is between 0 and 1. So we have 0, 1, and 1, 1/4. So this is the decay graph getting closer to 0. And then we get to shift it. Left 1, very good. This goes left 1 and up 2. So I'm going to take this point and go left 1 and up 2. Left 1 and up 2. It had an asymptote at 0 and it got shifted left 1 and up 2. So where is my horizontal asymptote? At 2. It got shifted up 2. So we have an asymptote at y equals 2. So make sure you draw your asymptote first because you cannot cross it. And then your decay graph. The domain is negative to positive infinity every single time, ladies and gentlemen. What's the range? 2 to infinity, whatever this happens to be. The k is your asymptote, helps with your range. Y equals 2 is the asymptote there. Questions on those? Do you need any more or is that good? It's good, right? It's good? Okay.